All right. Okay, so this term I'll be teaching Introduction to Quantum Information Processing. I'm John Yard. This is where you can find me. Here's my email. And classes will be held on Tuesdays and Thursdays starting at 2 p.m. over in the Quantum Nano Center, 1201. So the goal of this course is to give a general overview of the theory of quantum computing and quantum information at the graduate level. So the contents will be we'll start off with doing an introduction to the quantum information framework. And this will include some study of quantum algorithms and quantum complexity theory, such as Shor's famous factoring algorithm and Grover's search algorithm. And we'll discuss some basic introductory topics in quantum information theory, including density matrices and quantum operations on them. These are some generalization of probability distributions and conditional probabilities. We'll study distance measures between quantum states, entropy and noiseless coding, and also quantum error correcting codes and fault tolerance, which are important topics for trying to construct a quantum computer. We'll discuss some basics of the theory of quantum entanglement. So entanglement is some sort of a non-local correlation between separate systems that has really no classical counterpart. And an application of entanglement is quantum cryptography. And so we'll discuss the BB84 quantum key distribution scheme, among others. So just some general course information. So roughly the background will consist of linear algebra, mostly over the complex numbers, so unitary Hermitian matrices, some basic probability theory. And it's helpful but not really required to have some exposure to classical algorithms and complexity theory. And along with that comes some mathematical maturity and willingness to follow abstract arguments. So you'll be evaluated on 5 assignments worth 12% each, so that's 60% of the grade. And 40% of the grade will be a project consisting of a paper written by the end of the term. And here's some recommended text. It's not required, but you may find them helpful. So just to start off on what some of the theory is going to be about. So we have ordinary probability theory, where suppose you have some sample space, you have some probabilities which are non-negative numbers that add to 1. And so for example, if you have 3 elements in your probability space, the different distributions you have form a probability simplex like this. So your different distributions are some vector on here, given by, like here, vector in R3. And so if you sample from such a random variable and you observe the outcome, you get outcomes 1, 2, or 3 by taking the inner product of this vector with one of these 3 vectors that corresponds to the 3 outcomes. So in quantum mechanics, it's a little different. What we instead have is we have probability amplitudes now. So we have sort of the same sample space, but now we have some complex numbers whose absolute values squared sum to 1. And so what we get is we get a quantum state here that is some vector in a complex vector space. And when we perform a measurement, and we'll go over more of the details of this in class, you get some outcome with a probability given by the square of this amplitude. And you kind of turn a quantum state into some probabilistic state via measurement. So another valid operation that can show up in quantum mechanics that doesn't arise classically is that you can actually rotate a quantum state into another one. And this is modeled by some unitary matrix. This is something that preserves the complex length of a vector. And different rotations can give you different probability distributions after measurement. And so the types of quantum interference effects that you may have heard of, they essentially result from these types of operations. Okay. So as far as algorithms are concerned, what we imagine is a computer consisting of some binary registers known as qubits. And so for n qubits, the state is actually given by some vector in a 2 to the n dimensional complex vector space labeled by bit strings like this. So this is called Bra-Ket notation. We'll go over this in class. And the idea is that each elementary operation or gate acts as some rotation on a 1 or 2 qubit system. So you imagine here time going from left to right. You have these different interactions, 1 or 2 qubit gates. And in the end of the day, you do some measurement. And so inherently, these types of computations are probabilistic. And it's kind of a generalization of probabilistic computation. So in kind of the way that the quantum information framework works is that we'll study various things that arise in that setting, such as we'll see that you can achieve information theoretic provably good security with short keys, that there exist known fast quantum algorithms for some computational problems, such as factoring. And in some cases, we even have the ability to prove that quantum computers can solve certain problems faster than conventional computers, at least in certain models. So one reason for our interest in this field is that there's been a lot of recent experimental progress, which has been leading to a rapidly growing industry really over the last few years that may actually be bringing quantum computers closer to reality. But a big obstacle in that setting is dealing with quantum mechanical noise. And a good framework for modeling that and dealing with that is quantum information theory. So quantum information theory is a generalization of classical information theory that treats it as a proper subset. And besides being a framework for modeling and overcoming quantum mechanical noise, it generalizes certain notions such as error correcting codes. There's a theory of quantum error correcting codes, which we'll kind of study the basics of in this course. And notion of entropy generalizes and data compression. And so classical correlations they generalize to more general types of correlations known as entanglement. So that's all I have to say. Are there any questions? All right, well, thanks.